that one. Which one? Oh, that one that we were talking about?
He's gonna see us before.
Yes, I attempted it and I did not know about the same answer. You did?
I did the work.
Didn't?
You did.
I started with the today and
Start with the arrow prop.
How would you do that?
What, my sneeze? Normally they're pretty like mild. This one was contained.
Oops. All right, so on our website, if you haven't looked or you need any of these things, you go through the week. I think on Monday, I posted under Monday's date here, I posted the business packet and its answers. On Tuesday, I didn't post anything. On Wednesday, I had these review notes, which is exactly what you're seeing here. This page, and this page with those kind of steps, that kind of thing. Under Thursday, yesterday, I have the Anton packet and the answers to the Anton packet. And then on today's, I'm going to give you some additional problems out of that packet, both some optimization, some related rates, and so on. Under Friday, that's January 8th, but under Friday, today's date, I'll have posted those additional answers, so you can use those as review. Okay, as you're getting ready for this quiz. So let's start with, so the three things, obviously, again, whoops. So we've got parametrics, right? So we've got to be able to use these formulas here with a parametric kind of problem. So we'll look at that a little bit, and then I'll give you some time to work on one. We'll kind of review real quick with a calculator. You use your calculator for everything on the quiz, but of course you got to show your work. If you're doing a derivative, if you're setting up an equation, you're trying to maximize, and you have that on your paper. If you're going to do the derivative, calculator can do it, but write it down. Write down what the derivative is, set it equal to 0, right? Shows me you're solving, then you solve with your calculator, all that stuff. So you write down what you're doing on the calculator, what you're solving, what you're plugging in. If you're doing a list of candidates, you're plugging numbers back into an original function. If you've got C of 0, C of 6, or whatever, you can then on your calculator plug the 0 in, plug the 6 in if you need to, whatever, but you got to write down that that's what you're doing. That's what C of 0 tells me, right? That tells me you're putting a 0 in to your C function that you have or whatever. Okay, so list of candidates or number line or whatever, it's all labeled, and you have all that work there. Your answers, make sure you have units, make sure you have proper signs. One that sometimes gets people is, let's say you were doing a related rate problem, and the answer came out to be the ladder was falling down the wall, right? The question was, how fast is it falling down the wall? And let's say you had a picture. Oh, oops, I'm recording here, so better do it up here. So let's say you had this ladder and it was falling down the wall, and you labeled this X and you labeled this Y, and the ladder was 6 feet or whatever. And at the end, and so the ladder was falling, at the end you came up with Y prime was -6 feet per second. Okay? Now that would be an okay answer right there. I've had people write out their answer too, because the question might have said, how fast is the ladder falling down the wall? And some people will write out, the ladder is falling, the ladder, or no, it might be, the question might have been, find the rate that Y is changing or something like that. But so I've had people say, well, the ladder, the height the ladder is up the wall is decreasing at -6 feet per second. So what's wrong with that? Well, it's like a double negative, right? Like a double negative. So you'd actually be saying it's increasing, right? So either say that y is decreasing at 6 feet per second, or say it's changing at negative 6 feet per second. Does that make sense? Don't do both. Don't say it's decreasing at negative 6 feet per second, because technically that's not correct, right? So I always feel bad about that, because here's somebody's trying to go the extra mile and write out, what's happening, and then they kind of say it wrong, and ends up maybe costing them. So, but then of course the safe bet is just to answer it like that, right? Just say negative 6 feet per second and just leave it at that, okay? But if you're going to use the word decreasing, then don't have the negative as part of your answer. Okay, that's just a small thing, but just trying to think of some of those kinds of issues that could come up. But be sure you answer the question, and so forth. There's probably, I think, there's going to be at least, one parametric problem, or 2 or 3, I don't know, but I want you to do all these things. So I can give you one parametric problem and then ask you a bunch of different stuff about that one problem. Or I can give you one problem that asks you about these things, and maybe another problem, a different parametric to ask you about speed and that kind of stuff, whatever. But you're going to have to do these things probably at least one time, right? Whether it's in 1 or 2 problems or whatever. Probably going to be at least a couple of kind of max min kind of problems, right? Probably going to be at least a couple related rate kind of problems, right? So each one, so could be as few as 5 problems, right? But each one's worth 6 points, maybe, something like that. Your state. Did you set up the equation? Did you do the derivative, set it equal to 0? Did you do your list of candidates? You get the partial credit as you go along. Of course, if you don't get it set up at all, it's hard to get any of the points following, right? Now, the plan is for most of those to be like ones we have done the most in our homework, right? We've done a number of cone problems. Optimization, we've done several of the business. We've done a fair amount of business problems, or maximizing area maybe, or something like that. So we've also spent some time on some of the off-the-wall ones a little bit, that are the swimming pool with all of its different pieces. Probably not nearly as much of that. Now will there be a part of one, or one that's, more challenging than others? Possibly, right? But there should be a fair amount of problems on there that are pretty basic. I mean, pretty much follow the steps and not horrible to set up, if you've been doing the homework and going along. Okay? So, let's take a look at a little bit of the arrow problem here and look at what things are in there. Now, for the most part, I want you to be able to work with a parametric equation that I give you. So it's nice if we can explain where these equations come from, but you're not going to have to make up your own parametric equations. I plan to give those to you. So give you an x equation, give you a y equation, right? You can put those in your calculator. Now, some of you got thrown off here by this pi 12s, cosine pi 12s. The t is outside of the parentheses, right? If the t was inside the parentheses, that's a whole different ballgame, right? Then you got a cosine function. But all you have here is 150 times cosine pi 12s. So that's just, let's see, I did that here on my calculator. 150 sine pi 12s is just that. And 150 cosine, where's my trick stuff? Cosine of pi 12s is just that. So back here on this paper, that's just, so this equation is really just like x equals, this is just x equals, what was cosine? That was 144 something? 144 point something, I think, t. And then the y equation was simply 4 plus 38.8 t minus 16t squared. I mean, that's all those equations were. 150 sine pi 12s and 150 cosine pi 12s is just, those are just numbers. Those are just numbers, okay? Now explain where those come from. Well, if you launch a projectile at a 15-degree angle at this velocity, this would be its, I don't know, call that C, call that distance C, I'll call this X. This would be its, that would be its horizontal and vertical velocities. Okay, it would just be right triangle trig, right? It'd just be the cosine of 15 degrees would equal X prime over 150, right? It'd just be the adjacent over the hypotenuse. So you multiply both sides by 150. So 150 cosine 15 degrees is your X prime. So that's where that came from. Okay. Now, if I do the antiderivative of X prime, what should that give me? What's the antiderivative of a number? What's the antiderivative of 7? Or in this case, 7, what's the input variable here? T. 7t, right? So the antiderivative of 150 cosine 15 is 1, which of course is pi 12, is 150 cosine 15 times t. That's where this X equation came from. Plus some constant, which would be its horizontal position, and we're just saying that this is starting at 0, I think 4, isn't that what they said? It was shot from a height of 4. So it's shot from, so its initial X position is 0, so that's where that 0 came from. And on this one, now where'd this come from? See, now you got to bring in gravity. So on this one, what is Y prime? Well, sine of 15 degrees would equal Y prime over 150. So Y prime is 150 sine of 15. However, you also have to take into account that's its vertical velocity that it was shot at initially. So it's got, since it was not like the baseball, which we threw horizontally, right? When we initially launched this at 150 feet per second, it's got some horizontal velocity, it's got some vertical velocity. So right as soon as that arrow releases, gravity starts pulling on it, right? So what you have is you have this vertical velocity was shot at minus, now what's gravity in feet per second? No, that's meters. 32 feet per second every second. So vertically, it's going to lose 32 feet per second every second. So minus 32t. That's where that comes from. So it starts. So it starts with this velocity vertically, but as soon as it's released, gravity starts decreasing 32 feet per second times every second, and that's why there's a T on it. Okay? Yes?
Do they have to memorize gravity?
No. So, because as I said earlier, you're not going to have to come up with these, but I'm just talking about this explanation right here. So where do these come from? So now if Y prime is that, then we would do the antiderivative of that. Right? So the antiderivative of that would be, okay, that's just a number. So what's the antiderivative of a number? The number with a t on it, right? So it'd be 150 sine 15 degrees times t. What's the antiderivative of negative 32t? Negative 16t squared plus c, right, which is your initial height, which the initial height was 4, and that's why the 4 is in it. So that's where those equations come from. So they're pretty easily built. If all you know is that, and you know this angle, then right triangle trig gave us this, and then understanding about gravity and those kind of things, and then doing antiderivatives gave us that. That's where those equations come from. Okay? You're not going to have to do that, right, on this thing. I'm going to give you what these equations are. Okay, graph it, sketch the graph. Will it hit the target? Well, will it hit the target? Let's talk about that. The target's what, 3 feet high? What did it say? 5 feet high. And what was the 3? Is there no 3? That was the diameter of the target, right? So that means what? When the arrow gets there, here's the ground. What would be considered hitting the target?
3.5 to 6.5.
How much?
3.5 to 6.5.
Because right in here we said was 5. So the center of it was 5 feet. And the diameter is 3. Right? Did everybody read it that way? Center of the target, is that what it said was 5? Okay, and diameter's 3, so 1.5 up here, 1.5 up here. So it's y, so the y value has to be somewhere between there. So that's what we're looking for is the y. Now we got a y equation, right? So what do you have to do first? Well, we launched the target from over here. Actually, we launched it from up here. Right? And it's going to do that. So what's the first thing you got to do? First equation you got to solve here. Just like we did with the baseball. In what equation? The x equation. We want x to be 100 yards, which is 300 feet. So we're going to plug a 300 in for x, or 300 in for the x, and we're going to set that equal to the x equation, right? The 150, what was that, cosine t, cosine pi 12 times t, and we're going to solve that. And that would give us the time it gets over here, right? And then what are you going to do with that time? Plug it into the y equation and see what you get. Did it hit the target? What'd you get? Everybody get that? I don't have the answer. Really? It was way high. Way high. Okay? All right. But again, same kind of thing was the baseball a strike. We did the same thing. We said how far away was it? That's the x value. We found the t, the time when it gets there. Put that into the y. That tells you how high it was. Okay? All right. Next one. How high does the arrow get? So here's a couple of questions I got from people. So we got this. The arrow's launched. It's going like this. Aren't you looking for that point right there? Now what has to happen right there? Okay, so one way to do it is the slope of a parametric path. What's the equation for slope of a path? Y prime over x prime. So some people ask me, do you have to do that? I say you don't have to, but you could, right? When is the slope 0, which is y prime over x prime? But when is a fraction ever 0? When the top is 0. So you really only have to do that, don't you? You really only have to solve that. Okay? And actually it makes sense because when we want to know how high it gets, we want to know when it quits going up. So we want to know when its vertical velocity is 0. And remember, when we go back to this, vertical velocity is y prime. So we really only care about y prime when we want to know how high it got. We want to know when y prime was 0. So that's really all we had to deal with. We really didn't need to do the slope equation, but it is the same thing. The slope is also 0 up there. So when is this 0? Well, that's 0 when the top is 0, which is y prime. Okay, so either way of thinking about it is going to get you there. All right, and then what about this one? When is the arrow the fastest? So I talked with several of you about this. This is kind of a combination kind of thing. First of all, what are we talking about with the arrow here? Speed. And don't we have an equation for speed? But we want to know when it's the fastest. So what is that like? What's that asking really? Say that again. Maximum, right? Isn't this really a maximum problem then? It's kind of a combination problem of the things we've been learning. It's really an optimization. And step 1 in optimization is identify the thing you're trying to maximize. Well, it's a speed. So the second step is write an equation for speed. Oh, we got one. It's this, right? Right? So we've got x prime. So you got x and y. So you do x prime, do y prime. Plug those into that. And you've got a speed equation. And now it turns into a max problem. So how do you find the max? S prime, which is going to be something big and ugly, so do it on your calculator. Set it equal to 0, right? Find those points where it is. Where is it traveling the fastest? Which is when it hits the ground, isn't it? I mean, because what's going to happen, I think if you find that's when it hits the ground, because what's happening is as it starts falling, it starts picking up speed, and picking up speed, and picking up speed, and picking up speed until it hits the ground is when it's going to be the fastest. Okay? But you can find it by, it's really a maximum kind of problem. Okay, while we're talking about parametrics, let's just do this one right now. So get your calculators out. And let me just give you a pretty simple one, and let me ask you some questions. So here is, so this is like the pitch. This is like when we threw the pitch, right? So go ahead and, I didn't say to graph this one, but let's graph it. Okay? Let's graph it. So this is like the baseball player throwing the ball from a height of 7 So I'm not going to give you the window. I want you to figure it out. But I might give you the window on the quiz, but I might not. Right? Might give you some information about it so you could set your window. Okay? So this is like the baseball player, 7 feet off the ground at release, throwing it horizontally at 150 feet per second. So go ahead and draw yourself a little picture of that. Try to get it on your calculator, get a window. Answer those first 2 questions. Work together if you want here, or help each other out, whatever. But these are the kind of things I want to make sure for sure you're going to be asked this on the quiz Monday, right? Those things that are in our notes. So if you want to double check with someone, go ahead. Okay. If you got a question, I mean, that's kind of why we're doing this. If you got a question about it, type in your calculator or set your window or anything, let me know here. Or ask somebody next to you. Now, if I'm going to really ask you to draw a sketch, on your paper, I probably would give you the window so everybody would be looking at the same screen. But if you're just drawing a sketch to help you, zoom fit maybe, or just something. Of course, remember to go to parametric mode. That's obviously key. Okay, the last question here. Oops. Okay, last question is that. Okay, I think I can squeeze them all in there. There we go. Okay, so I put the equation up on the board, and there's the three questions, okay, we want to do. Caleb, make sure you're logged in too. It was 60.5, right? The distance from the release, yeah, thank you. From the release to home plate, right? From the release to home plate was 60.5 if you need that. Oh, of course it won't. Of course it won't. Okay, now try again.
So the X would be. Oh, I did not.
Yeah, it's from the. Yeah, me too. I did it backwards. Dang it. Yeah. Yeah.
Yeah, 0 is where he's pitching. Right. That's another thing that we would do that I would ask you probably, if I asked you to sketch a parametric graph, would be to mark the direction of travel, like with arrows, label maybe certain points, like at t equals 0, t equals 1, like this would be at t equals 0 right here, So you could label, kind of like some of the graphs in the book were, that kind of thing. Okay, Caleb, how you coming? You got them all?
He's almost there.
Almost there.
He's horizontally no conflict.
Yeah, that's right as well.
Okay,
So
no,
that's 5, 100 equals 552.
yeah. I think I did check wrong because when I took the derivative, I left the 7.
Oh,
So I need to get rid of the 7. Okay, 1 second. Negative 0.0576. Yeah. Yes. Okay.
All right. First of all, as Caleb's finishing up there, it looks like, and some of you have finished, find the velocity of the ball when it's 3 feet off the ground, horizontal velocity of the ball. What'd you get?
I got 150.
150. What's the horizontal velocity when it's 4 feet off the ground?
150.
2 feet off the ground.
150.
Forever and ever and ever, the horizontal velocity is 150. Remember we talked about the ball, no friction, but who cares? Even if you didn't understand it was a ball, whatever, horizontal velocity is x prime, right? Horizontal velocity is x prime, right? I mean, it's the number one thing in the notes. You got to know. Horizontal velocity is x prime. So there's x, do x prime, or dx dt, derivative with respect to t, it's 150. All the time. So there's nothing to plug in. You might be saying, well, why did you tell me the 3, right? There's nowhere to put it, nothing to do, right? It's x prime. Now, if that would have come out and had a t in it, then yeah, then you'd have had to find the time when the ball was 3 feet off the ground. So let's talk about that, just in case, right? Maybe it wasn't quite so simple, right? Maybe this was a more complicated equation. You did x prime and had a t in it, and you'd want to plug a t in there. Would you plug a 3 in for t? No, that's not time. 3 feet off the ground would be what?
X. Y.
That'd be the y. 3 feet off the ground would be the y. So you would plug a 3 in for
Y.
right there, and you would find what t gave you that. And then that t would go over into the x prime, right? So that problem could have been more difficult with a different parametric equation, right? So understand that. So the 3 could have been important. 3 feet off the ground is the y, so 3 would go right there, solve it, take that t, plug it into there. But as it turned out, it was 150. Okay, what about the speed of the ball? Caleb, what'd you have there? So isn't that the equation right there? X prime is 150 squared, y prime is that squared, and then you plugged in what, a 0.25? And we talked about how this is that weird problem where the ball actually gets faster. So 150 point, what'd you say? 213. Okay. So you just plug those values in. So let's look at that on your, since I had you be the presenter, let's go to your calculator screen. Let me see that. So arrow up there, you got it somewhere, I suppose. Now right there. Okay. All right. So you just put that in there. Okay. Then, the next part, of that, find the slope of the path. So there's using the speed equation. Now I made that a little easier in that I just gave you t, right? I just gave you the t, so you just plug it in. But again, I might have said, find the speed of the ball when it's 3 feet off the ground, right? Well, then again, you'd have to put a 3 in here, find the t value when that happened, and then you'd have plugged that in. Right, like we did before, find the speed when it crossed home plate. Well, you first had to find the time when it crossed home plate. And that's where we put a 60.5 in for x, and then found the time and then plugged it in, right? So you have to be able to use these equations. Okay, find the slope of the path of the ball when it is 20 feet horizontal from home plate. So I did this on purpose. I heard some talk over here, but figured it out later. So what is actually what you have to plug in? You don't put 20 in for x. You put 40.5 in for x. When the ball, did you do 20, Caleb?
Yep.
Yeah, okay. When the ball is 20 feet from home plate, now notice I said horizontally, because technically the ball's up here, right? So if you say, how far is it from home plate, you might be thinking that direct distance, right? And I want you to understand that we're talking about horizontally. It was 20 feet from home plate, so that's why I threw that in there. So 20 feet from home plate would be right here. Well, that's an x value of 40.5 because x is measured back from where it released. Okay, so you got to be aware of that, right? You got to be aware of that. So actually, we're going to put a 40.5 right there for x. So 40.5 equals 150 t. You're going to divide by 150, so you get t equals like 0.2 something. 7 something something. Keep all those decimal places. And then we're going to plug that into y prime over x prime, right? Which would be negative 32t over 150. So you'd plug that value into there. And what do we get? Emily, what I know you guys were doing that negative.
You get a 0.058.
It's pretty horizontal. This ball's not dropping very much, and so we expect a pretty small slope. Now we would expect the negative. Okay, very good. So that's most of what would be another thing I could ask you. I'll tell you what, now that you've, let's say I asked for the horizontal and the vertical velocity at 0.25. So when t equals 0.25, tell me the horizontal and vertical velocity. This is the other question I can think that we've talked about with parametrics. Give me the horizontal and vertical velocity. So what would the horizontal velocity be? 150. What's the vertical velocity? Right. What is that? -8 feet per second. What do those two answers tell me about the ball? No? Well, no. No. What do those two numbers tell me about the path of the ball? Let's put it that way. It's going right and down. Horizontal velocity is positive, means it's going right. We did that with Adam Ant, right? Where, if you had a positive horizontal velocity, it's going right. Negative horizontal velocity is going left. Positive vertical velocity going up, negative vertical velocity going down. So the ball is going to the right as we look at it and down. So those are some of the questions, really a lot of the different questions I could ask you about that. Okay, let's go to Anton's packet here. And I want to look at one of the problems I want to do, one of the things I kind of promised I would do today is do an optimization problem all the way through. And so one of the Anton's problems I would like to do today was the one with the wire. Would that be a good one to do? Okay. Let's do the one with the wire. Number 14. It says a wire of length 12 inches can be bent into a circle, bent into a square, or cut into two pieces to make both a circle and a square. This is 14. Second page. Page 348. I don't think there's another 14 that's circled. So. Yeah, it's the only 14 that's circled. So I can cut a 12-inch piece of wire into a circle, or excuse me, I can bend it into a circle, I can bend it into a square, or cut it in two to make a circle and a square. How much wire should I use for the circle if the total area enclosed by the figure is to be, let's do maximum first. If I'm going to do a maximum, okay, all of it should be used for the circle.
Yes.
Why? I would agree with you. Right? I mean, if you remember, we did the problem. If you had a certain amount of fence and you wanted to build a rectangular pen to hold your cattle, right? What size if we said a square, right? But if you could pick any shape to maximize the area for the least amount of perimeter, it would be a circle. It would be a circle, right? Now, that would get you no points on the quiz if that's what you did. If you said a circle and it's just a geometric fact, right? Because you get points for showing the calculus of why it's a maximum, right? So he's correct. That is going to be the answer. Okay? So let's set this up as why this would be. So here's my piece of wire. Okay? It's going to be 12 inches. Let me draw my circle plus my square. Now, this is kind of like the snowmobile or the person stuck in the woods, and it's like the power line situation, right? I mean, one option is to just go straight through the woods right to the gas station. Another problem is go straight up to the highway and go there, or there's some in between. Well, that's kind of what we have here. So that's kind of like our endpoints. We can go all circle, all square, or a combination of both. Well, let's say we go a combination of both. Okay? So we want to, number one, identify. What are we trying to maximize here? Area. So step 2 is write an area equation. So what's an area of these two added together? Pi r squared. Okay, you want to label those as x, that'd be fine. And label that as r. So there we go. That's step 2. Step 3 is try to get that in terms of one variable, right? We don't want to do right? I mean, this is not a related rate problem. We're not talking about how fast these are growing. We're not doing the derivative with respect to t. We're not doing primes and all that. That's not what we have. We want to find when the area is a maximum. So somehow we need to get these in terms of one variable. Well, what we have is this piece of wire that's going to create these, right? So let's say we cut, the piece of wire, say here. So now we're using x for this, so we can't use x for that, so we'll use w. So let's say we cut this piece w, and then what would be left? 12 minus w, right? That's the piece we would have left. So if we're going to let w be what we use for the circle, right? If we want to let w be the amount of wire we use for the circle, okay? Then how could we? What would we know if we took this piece and we wrapped it into a circle, right? How could we set that up? 2 pi r would equal w, right? So how could I use that? And then what's left, this piece, I'm going to make into the square. So the 12 minus w is going to go for the square, right? So what does that mean? 4x is 12 minus w. Correct? That's kind of like my extra information. So what could I now do with that? solve and make it into, and which one will be my one variable? W will be my one variable. So on this one I could solve for R, and I'd get W over 2 pi. And this one I could solve for X, and I would get 12 minus W over 4. Does that make sense? So I'm going to take that piece of wire, cut it into 2, so one, and I don't know where I'm going to cut it, so W and then 12 minus W would be what's left, and I'm going to do that, okay? So now my area equation is going to be pi times W over 2 pi squared plus, and then X, that's 12 minus W over 4 squared as well. Now I've gotten to the red line. I've gotten through step 3. Now I could simplify this a little bit if I wanted to, but we can also use our calculator. Now I'm old school. I'd rather simplify this a little bit, but you wouldn't have to. But this would be W squared, and the bottom would be what? 4 pi squared. And this would be W squared. Now, wouldn't one of those pi's cancel? Right? So I'd have W squared over 4 pi. Right? Let me do some red here. So this pi would cancel one of those pi's. So I'd have W squared up top, and I'd have 4 pi on the bottom. Okay? And then plus, and then I don't really want to, I'm going to square the top. That's 12 minus W all squared, and then the bottom would be 16, maybe. That at least simplifies that a little bit, but if you don't trust yourself, let the calculator do it, whatever. Okay, so that's what I'm trying to maximize. So now what? Do the derivative. So let's do that on your calculator. Do it with, you can type in a W or you can change it to an X right now if you want. You know, when you type in your calculator, use X or use W, whatever. But if you use W, you got to do the derivative with respect to W. Okay, so let's type that in, see what we get. So my goal here right now is to actually have went through an entire optimization problem. We haven't done one where we went through the whole list of candidates and endpoints and everything. I mean, I've kind of left that to you a lot, but so I want to go through one here from start to finish. Okay, according to the calculator up here, we get pi plus 4 W minus 12 pi over 8 pi. So I'm getting that. We're getting that as our derivative over here, is what the calculator is telling us if you type it this way. But depending how, if you left it the way it was originally, maybe yours looks a little different at this point, whatever, just write down what your calculator's got, that's fine. Okay, now we're going to set that equal to 0. Now, is this ever undefined? What does that mean? When it's undefined when the bottom is 0. Will the bottom ever be 0? No. Okay, so A prime, never undefined. If it was, we would figure out where it was undefined. Usually that would mean taking your bottom and setting it equal to 0, right? Finding out where the derivative is undefined would normally mean taking the bottom, setting it equal to 0, doing a solve. That's when it's undefined. Then that would be one of your candidates to plug into your list of candidates. Okay, and so we go ahead and do this, and we get W equals 12 pi over pi plus 4. Okay, what is that as a decimal? Let's go ahead and see what that is as a decimal. Sometimes that's a little more meaningful. 5.279. That makes sense? Okay, now that's W. All right, so now that is, we have one candidate basically at this point, but what haven't we checked? Endpoints. So let's talk about endpoints. Now, what variable up there are we asking ourselves when we're doing endpoints? W. W is our input variable. We're asking ourselves, what's the littlest W can be? So look up here. What's the littlest W could be? 0. What would that mean? Means we didn't use any of it for the circle, right? Because W, we said, now we could have let W be the square, right? And then we would have been getting different numbers here. Our equations would have been looked different. We could have let 4x equal W, and we could have let 2 pi r equal 12 minus W. Then everything would have looked different, right? Because W would have been something the opposite, basically. Okay? So W is what we were saying we were going to use for the circle. So we could use none of it for the circle. That'd be 0. And then what would the most W could be? 12. And then that would mean we would use all of it for the circle. So what I like about this problem is this is a problem where endpoints really matter. Endpoints really matter. It's kind of like the power line problem, right? 0 meant we went all the way underwater. And 6 meant we went straight across the water and then all the way on land, right? So there are these kind of problems where the endpoints really matter. A lot of the times our volume problems, our area problems, a lot of times 0 meant nothing because that was a minimum. There was no area or volume. But here's an example of one where it matters. So we can really do a list of candidates now. Okay? So we're going to plug them into what equation? The A equation. So we're going to do A of 0. We're going to do A of 5.279, which we want to actually not round that when we plug it in. And then A of 12. Right? And we want to plug those back into our A equation. Now here's where, okay, I'm going to pick on you, Caleb. You're going to help us here. Okay? So now let's type that A. Here's where, now you could do this however you want, but this is one of the things I showed you, is that we got kind of this messy equation here, and we're going to plug these numbers in. So a nice way might be to just type this equation out using W. Okay, so let's do that, Caleb. Let's type that out. So let's go W squared, well, yeah, there you go. So what do we have? W squared for A. So we had W squared over, was it 4 pi? And then plus, and then what was this? 12 minus W quantity squared over 16. And then put a vertical bar at the end. Now what we really want to do is plug these W's into there. 0, right? So you could have just done that. You could have done 0 squared divided by 4 pi plus. You could have just done that manually for each one. But now we're going to do that vertical bar. And he's going to put W equals 0. I would hit Control Enter. Oh, it came out exact. Okay, and now we're going to now arrow up and grab that. Now we want to plug in a 12. So he got 9 for that one. And now let's plug in a 12. Give me a decimal on that. 11.459. And then the 5.279. Now it'd be good to use, what was that number? 5.27881. That get at least a few more decimal places there. Okay, and what do we get there? 5.041. Okay, so now haven't we answered both of the questions, really? We wanted a max or a min, but now you got to kind of decipher this now. So our max area, the question was, how much wire should we use for the circle, I think. Wasn't that it? How much wire should we use for the circle? So that's good, because that's what we let W be, right? W is the wire we're going to use for the circle, so that's good. So the max was if we use 12, which is what Jamie told us, right? If we use all 12 inches, so we use 12 inches for the circle, that's our max. Right? They didn't want to know what the max area was, so I don't have to give them that number. I'm going to answer the question. Is that right? I'm sorry. I hit that. Okay. And the minimum is if we do what? 5.279 inches for the circle. So that'd be a part, have one circle, one square, that would actually be the minimum. Is if, okay, so that would actually be worse. So the worst case scenario for the area, the least efficient way would be to use part of it, okay? So that's the minimum, okay? And then the rest, use the rest for the square, okay? So anyway, I like that problem. Now that's, again, that's on the difficult end of the scale for setting that up a little bit because of what you had to do kind of with the wire and finding these secondary equations. Sometimes those are a little easier to come up with, like perimeter, you know, and some of those things. But that's how, what a good, you know, a good one that's got some candidates that you can use, you know, got endpoints that you can find and that kind of stuff. And it may look like, again, but we've definitely had some simpler ones, especially our upside down parabolas where they're maxes, where we've only had one candidate and we could do a number line or somehow we could, you know, or maybe we had endpoints that really made no sense and they just came out 0 and so, or one, so there could be those easier type ones and definitely have some of that on the quiz as well. Okay? All right, let's do, is there one related rate problem we can do together? And then I'm going to give you some work time here. From the packet that you had a question about. So that'd be on the first page, the first or second page. First page of the back. Either one of those. I mean, there's a cone, couple of cone ones there.
Let's do a cone.
Do a cone one. 26, a comment I would make on 26, that'd be just more of a Pythagorean theorem one, right? So that'd be an a squared plus b squared equals c squared. Those are pretty common type ones too, so you do the derivative from there, that kind of thing. Okay, but a cone one, we've done a few of those. Let's do one more. Okay, so which one do you want to do, 21 or 23? Doesn't matter? Okay, well, I'll pick them. 21. Conical water tank with vertex down. I'll probably help you if we have a cone one on what direction it is, but the water tank ones are vertex down, the sand ones are the other way. Okay? Has a radius of 10 and is 24 feet high. Now there's water in here, right? So the water depth is R and H, but the cone itself is that. Now what does that tell you right there? What does that help you in getting this problem solved? So give me the proportion. 10 over R, 24 over H. That'd be one way to do it. Another way to do it, R over H would be 10 over 24. But that information is there. Now in 23, it's easier. They just said the height is equal to the diameter. Well, height is equal to the diameter. The height would be 2R, right? Or R would equal 1/2 H. It's probably the way you want to write it. That would be 23. So 23 is a little more direct in what they tell you about. In 21, they just give you the dimensions of it, and then you've got to come up with the R and H. But that, to me, is really the key in the cone problem, is that R and H relationship. So 24R equals 10H, and we've kind of decided the one we like to solve for usually is R, isn't it? R is usually the one we like to solve for because that's the one we want to get out of there, right? So what's the volume of a cone? 1/3 pi r squared H. But now what can we do with that? We can take that and plug it in for that R. So we get 1/3 pi 5/12 H all squared times H. Let me give you just a minute to simplify that. This is, people sometimes get to this part and they decide to start trying to work with the derivative from there, and that's crazy. Crazy. what do you get when you multiply that all together? 25 pi over something. 432. And then there's an h cubed. I'd put the h cubed out to the side, quite honestly, but it could be on top, you're right. But to me, that is the best way to think of it when it comes to doing the derivative, because the 25 pi over 432 is just a constant. The h is the variable. H is what's changing here, right? And so I like to keep the constant out in front and then the h cubed over there, right? Okay, so now what? Derivative with respect to, no, not h, time, right? So dv dt, v prime, equals. So we're going to bring the 3 down in front. Now you could do the derivative, but now that's interesting. On the calculator, you could do the derivative here with respect. I guess I never talked to you about doing the derivative on the calculator with these, because you know, how do you do the derivative? I'm not sure even what the calculator would do if you typed this in and told it to do it with respect to t. I actually would probably do it. Yeah, I think it would treat the h as a. Well, Caleb, nobody's asked me about this. Has anybody done this on these? What's it told you?
I've used it on some of them, and it's just giving me like instead of writing h prime and being like d over dt.
So tell me, Macy, how you would type it. Would you put a t here?
Yeah, I was just typing it in C because I did this a while ago.
Put a t there, and then Caleb, go over here, and then I never thought about doing this. So put 25, do a fraction, and do 25 pi over 432, and then arrow right, and then put h cubed.
It just gives a 0. Yeah.
Yeah, see, because I think it treats h as a constant. Anything that's not a t, it treats as a constant. So that's not going to work. So what you could do is you could come back here, grab that again. You could do the derivative with respect to h, but gosh, I think that's going to be confusing to you because you're not doing the derivative with respect to h. But it's like what do we say in implicit? We say do the normal derivative and then tack on an h prime. So I suppose you could, but gosh, I hope you can just do this derivative without the and just bring the 3 down and just do it. But go ahead and hit enter. And there it did the normal derivative, right? It's got the h squared. And now you just have to remember to tack on a h prime. Now, I actually think it would work. Go ahead and grab it one more time. I think you grab this one up here, the one with t. Actually, I think what you have to do is, see, the calculator's treating the h as a constant. So but it's not a constant. What is it? It's a variable with respect to t is what it is. So if you went in here and arrow over here to the h, and then put parentheses t, Caleb, now I'd be telling it that it is and then put a right parenthesis. Now I'm telling it that h is actually a variable. Now hit enter. And now it does the derivative. And then see this dh dt right here? That's the h prime. So it actually did it there. But that might just be like, I don't want to mess with that, right? How many people say, I don't want to mess with that? That's actually, I never showed you that during implicit differentiation. But, so I'm hoping you're not that dependent on your calculator that you need it to do the derivative for you, because I think that'll just be harder for you. So you bring the 3 down in front, and now get your calculator out if you want help with that, and just do that on your calculator, right? Just bring the 3 down. Do that on your calculator. It turns out that it's 25 pi over 144 h squared h prime, right? That's the best way to do it, right? Okay, so you just bring the 3 down in front, use your calculator to help you do that, h squared, tack on an h prime. Okay, and then what do we do? I guess I left off some information here. They said that the water's going in at 20 cubic feet per minute, so what's that? Cubic feet per minute, B prime. And then it says when the water is 16 feet deep, that'd be H. So now you're just gonna plug your 16 in and your 20 in, and then you're just gonna find H prime. And we did a bunch of that the other day, and so I'll just leave that for you to finish, okay? All right, so I hope that was time well spent, just to go back through, your basic kind of, I know the optimization was lower, but we went through all of those steps, what an optimization would look like, a cone problem again, seeing that again. Okay, so some additional review problems for you. Page 274, that's the first part of Anton. I would say this is all in Anton now. This is all in the packet. Okay, would be 6, 8, 12, 22, 24. I think those would all be some related rate problems you could do. And then on the optimization side of things, 11, 42 would be a couple more kind of max min kind of problems you could do. I will post the answers to that up there as well. You can probably do some that aren't circled. I mean, some of them were outside a little bit of what we do, but there'll probably be some other ones in there you can pick and choose to do for homework. So I'll let you have the rest of the time here to check some answers. Ask me some questions. I know I would look at that clock one. I'd help some of you with that clock one with the minute hand if you had some questions about that. But if you'd rather just work on some other stuff, you can. That was one that some people asked me about this morning, so I don't know if anybody else wanted to talk about that one. Okay? All right.